Now we come to the main dish of this week. That is, we get back to doing calculus. Remember, what's the purpose of calculus 4? The purpose of calculus 4 is we want to generalize the method of Lagrange multiplier from calculus 3. In particular, we want to, there are two goals in our mind. We want to not only be able to handle equality constraint, but also inequality constraint. So we will be able to handle both equality and inequality constraints. Moreover, in the first week of Calculus 4, I show you an example for which Lagrange multiplier does not capture the maximum point because that point is a degenerate point, for which the gradient equals to the zero factor. So we will learn a way to capture and also handle this kind of so-called degenerate point, And then if you want a reference, this is really the second example we did in the first week of Calculus 4. But to do this, we're going to start from scratch. In particular, we're going to review what we have done in Calculus 3, but perhaps we're going to rephrase it in a much more fancy way. Let's look at an example. So we're going to do a little review of the method of Lagrange multiplier from Calculus 3. So this is a standard question from Calculus 3. Find the maximum value of a function subject to the constraint x squared plus y squared plus z squared equal to 1. So as usual, the first thing you're going to do is to let g, let g to be the constraint function. So g, in this case, is x squared plus y squared plus z squared. And then what is the method of Lagrange multiplier? That is, you're going to set grad f to be lambda grad g. And then from this, you obtain a system equation here, for which the first three equations really just come from the this equation, grad f equal lambda grad g. So this three equation really just come from the Lagrange observation. And then the last equation, x squared plus y squared plus z squared equal to 1, is the constraint itself. I'm not going to solve this with you, but there is a very good exercise. There is a very good exercise. But there is a question here. So, question. Let me write it down on the right-hand side here. Question. Is there a nicer way to package, this system of equation? The answer is yes. But how? This is actually a very beautiful observation by Lagrange himself. He let a new function L that depends on x, y, z, and also a new variable he called mu. Well, you can call it lambda, but then by convention we call it mu. And that equals to what? Equals to the function you try to optimize f minus mu times, times what? Times, what's the constraint? In this case, the constraint is g equals to 1. So he's going to multiply it by mu times g xyz minus 1. Why is that a nice thing to do? Because, note. If you differentiate L with respect to x, then what do you get? Well, then you get f differentiate with respect to x minus mu times, this bracket, differentiate with respect to x, you get just gx. And then you do the same thing with respect to y, then of course by symmetry you get fy minus mu gy. And Lz is fz minus mu gz. And what is the most interesting is perhaps, what about if you differentiate L with respect to mu? So firstly, this has no mu. So when you differentiate with respect to mu, this died, okay? And then the second one, when you differentiate with respect to mu, well, only here you have a mu, so it becomes just minus g minus 1. And what we're going to do is to observe that if you set all of this to be 0 and rearrange, then you realize that this is really just this system of equation. The only difference is, well, we didn't use lambda, we use mu, but that is just a convention. So this recovers the system of equation. Okay? And moreover, another key observation, what's the advantage of doing this? At least one advantage or one observation, okay, is that solutions to the system become critical point of this new function, L of x, y, z, mu. Because, okay, any solution of this system equation will satisfy L differential with respect to x equals 0, L differential with respect to y equals 0, L differential with respect to z equals 0, and finally L differential with respect to mu equals 0. So, solution to this system is effectively just critical point of this fancy function here. And this is the starting point of how we're going to reformulate the method of Lagrange multiplier in a more systematic way. And I'm going to recap this again on the next page.